Good afternoon, students. Again, I am coming back to in my lecture number part 5. In lecture number 1 and 2 and 3 and 4, we already discussed about the how many types of solids and how many types of crystal lattice are present. But in this lecture, we considered that how a particles are arranged in a solid, crystal solids. So there are basically 3 types of dimension, and we know that packing is basically in solids. The packing is generally in closed way. What is the mean of closed way? That means they have least intermolecular space. So if we look at here, we talk about 3 types of dimension. One is 1 dimension, 2 dimension and 3 dimension. So in 1 dimension, what will happen in 1 dimension? So in 1 dimension, the particles are arranged in a linear way, and each particles must be arranged in that way. Each particles touches the another particles. If we consider that the particles have spherical in shape, so these spherical shapes show each particle. So these particles touches to each other, and that's why they show a definite coordination number. What is the number? What is the mean of coordination? So we already discussed about that. Coordination is just a number which represent the neighboring particles. How many neighboring particles are touches to the spherical particles? So in this condition, coordination number 2 represent that these spherical touches by 2 adjacent particles. Okay. Second one is in 2 dimension. When we talk about 2 dimension, they are basically 2 types. In 2 dimension, the arrangement must be in 2 way. First one is known as square close packing, and second one is known as hexagonal close packing. That means in 2 dimension, 2 types of packing. One is known as hexagonal and one is square close packing. So how can we arrange the square close packing? So if we arrange particles in such a manner, the first layer and above the second layer, the second must be arranged in similar way just like first one, and the rest of the others layer also follow the same pattern which is designated by A. So what will happen here? The particles present in a definite order, and due to this, the arrangement is known as a square close packing. In square close packing, the particles is surrounded by 4 other particles. The particles is surrounded by 4 other particles. If we look at this sphere directly touches these 4 particles. So what we say here? We say that these particles are surrounded by 4 other particles and show coordination number 4. Okay. In second case, hexagonal close packing. In this type of packing, the arrangement is such a manner, that's why they acquire least intermolecular space. If we look at the first layer A and B, how can the B arrange? B arrange in between the gap of the particles, which is totally different. That means it is stacked over the first layer at the depth of the first layer. So B represent the different layer, and again the third layer which is similar to the first one. Third layer is similar to the first one. That's why they show same type of arrangement just like first one. and again the fourth layer is similar to second layer. So what will happen here, in this type of arrangement, the layering takes place in such a manner: A, then B, and then third layer, which is similar to first one, that is again denoted by A, and the fourth one is resembles like second layer, that's why it denoted by B again. So this type of arrangement is known as AB arrangement, and in this type of arrangement, any particle is surrounded by 6 other particles. Any particles is surrounded by 6 other particles, and that's why they show 6 coordination number. They show 6 coordination number. So this sphere is surrounded by 6 particles, so they show coordination number 6. They show the coordination number 6. So in 2 dimension, 2 types of arrangement, okay, square and hexagonal close packing. But when we move in 3-dimensional space, the 3-dimensional is totally different. Why? Because anything having length, breadth and height, that is 3-dimensional. So if we talk about 3-dimensional, the third condition, it is also 3 types, showing 3 type of arrangement. First one is AA arrangement. Second one is known as AB, and so on. And third one is represented as ABC type of arrangement. Okay, so in first one, AA arrangement. AA arrangement is originated just to follow by square close packing in 2 dimension. When we use the square close packing from 2 dimension and put it another spherical in a horizontal way and in a vertical way, if we arrange the both side, layer the both side horizontal and vertical, what we get a 3-dimensional structure. In this 3-dimensional structure, all the particles arranged in a definite manner, and they show AAA type of arrangement. That show AAA type of arrangement, which is originated from square close packing in 2 dimension. Okay, this sphere shows that they must arrange in a simple cubic structure. If look at there, this black marking shows the unit cell, and unit cell is a smallest repeating unit of any crystal solids. So this is the repeating unit. But if we consider another case, that is your AB arrangement and ABC arrangement, so AB arrangement, that is known as hexagonal close packing, is originated from in 2-dimensional close packing. So what will happen here, in this case, from 2 dimension, the first layer and the second layer are arranged in definite pattern, but when we put another layer over the first one, if this one is A layer and we put another layer on the first layer, if the first layer contain this type of arrangement, that is denoted coloring by blue color. If you look at the blue color, all the blue color balls are A arrangement, So when we put another ball, the another ball arrangement is different from the base one, that means your first A layer. How can be this possible? They must be arranged in a definite order. So first one, if you look at the here, in this ball there will be a vacant space, and these vacant space is known as voids or hole, and in case of hexagonal closed packing, it is denoted by a specific letter, that is A and B. If you look at here, the trigonal which have upward cross, which have upward marking, that is denoted by B, and the arrow which is towards downside, that is denoted by A. So there will be two voids. In first layer. A contain two types of void. One is A and one is B. Okay, one is known as A and second one is known as B. So when we put the another layer over the first layer, what will happen? The another layer, this black one, shows that they must stacked over a specific voids. Either they acquire B or either they acquire A. Either they acquire B or either they acquire A voids, and due to this A voids, they show two-dimensional. If you look at this diagram, A the first layer and B represent the second layer. So B layer present in the arrange in A voids of A layer, in a void on the voids of A layer, and that's why they arrange in a definite pattern. So then we get another two voids, that is denoted by C and D. This C voids, this one is C voids, and this C voids is specifically tetrahedral voids, is known as tetrahedral void. Why we say that tetrahedral void? Because it is formed by four particles or four spherical structure. So these voids are known as tetrahedral voids. Okay, look at here, this point shows the tetrahedral voids. If we took in other side, this show the tetrahedral voids in which A layer and B layer. B is the another ball which stacked over the voids of A, and due to this void is formed as, and this void is known as tetrahedral voids. This void is known as tetrahedral voids because 1, 2, 3, 4, there are 4 particles. Okay, so but in case of D, if you look at the D voids is totally different. Why? Because they must be formed by the addition of two different voids. That means if the voids curve, look at it here, if the void curves, first one is this one, so the another face is that one, D voids. This is known as D voids. I think you get it. That means D void are formed by the submerging of two voids, that is A and B or A or C. So this one show that A and C type of arrangement, and this form D voids. And the specific structure of D, look at here, this structure shows the octahedral voids, in which the six particles surround to each others and form a octahedron. But if we consider two tetrahedrons, basically combine to each other and make a formation of octahedral void. One octahedron is above the plane and another octahedron, tetrahedral hadron is below its plane. So one is above and one is below. One is above and one is below. So that's why they show specifically octahedral voids. Octahedral voids, and this arrangement show hexagonal close packing. Okay, so if the third layer are arranged at tetrahedron voids, then it forms HCP. Then it's form HCP, hexagonal close packing in 3 dimension, and showing the arrangement of ABAB type of arrangement. So this ABAB type of arrangement is hexagonal close cubic arrangement, whereas ABC is cubic close packing, also known as CCP, and this is known as HCP. This is known as HCP. So HCP is formed due to when the third layer acquire the tetrahedral voids. But if the third layer acquire octahedral voids, that is your D, then it forms ABC, that is CCP type of structure, that means cubic close packing. So cubic close packing is ABC type of arrangement, whereas hexagonal close packing is ABAB close packing arrangement. If we look at the diagram, this shows that hexagonal close packing, and in this diagram what will happen here, this particle is surrounded by six particle which is present at the same axis, same layer, but they are also touches by these three particles. That means below its plane, and 3 other particle which is above its plane, and that's why these particles have coordination number 12. These particles have coordination number 12. That means in HCP as well as in CCP, both the particles show the coordination number 12. I think you get it. So how can they possible they are showing the 12 coordination number? 6 from the same layer, 3 from the below, and 3 from the above. Totally 6 plus 3 plus 3, that is your 12 coordination number. Again, it happen in CCP, that means closed cubic packing also. Okay, so if you look at here, closed cubic packing, so this arrangement is known as CCP arrangement. That is your this is represented in a long way. This is represented in a better look. That you show that 1 is surrounded by these particles. 6 are co-originated, 3 in above and 3 in below particles. Okay, so in both the cases CCP and SCP must contain coordination number 12. Okay, so this type of packaging you get it. That means in 1 dimension, 2 dimension and 3 dimension. So they show mostly coordination number 2, 4, 6, 8 and 12. They show 2, 4, 6, 8 and 12 type of coordination number. Okay. Okay, our next point is packing efficiency. What is packing efficiency? In any crystal, the particles are arranged in a definite manner. If we consider any crystal, the particles arranged in a definite pattern or definite manner, that they occupy maximum space and give least amount of spaces. These least spaces or holes are known as voids. This is also known as holes or voids. So what we say here, packing efficiency, that is the percentage of total space is occupied by the atom or particle is in a crystal is known as packing efficiency. The percentage of total space is occupied by the particles in a crystal is known as packing efficiency, that is denoted by PE. So what we say here, packing efficiency is equal to volume occupied by the atom divisible by volume of unit cell. Volume occupied by the atom or particle divisible by volume of unit cell into 100. So that is your packing efficiency. So if we talk about packing fraction, that is the fraction of atom occupied by the total space, that is known as packing fraction. Is that clear? So we calculate for first one is simple cubic cell, packing efficiency for simple cubic cell. So in simple cubic cell, the atom or particles are present at the corner of the unit cell. The particles present at the corner of the unit cell. If the distance between the two edges is A, if this one is A, and if you look at here, these particles are represented like this. So this one, the center area, this is R, and the total distance is D. Total distance is D. So for this condition, if we consider these particles are present like this, so this one is R and this one is R. So what we say here, A is equal to 2R, or R is equal to A by 2. R is equal to A by 2 for simple cubic cell. That is the relation between the radius and edge length for simple cubic cell. But when we consider the number of atom, the number of atom for SCC is equal to 1. You know that how 8 into 8 by 1, 8 corners, and the sharing would be 1 by 8. So the number of atom present in simple cubic cell is 1. So the volume of one atom or sphere, what is the volume? Volume of one particle which is spherical in shape, sphere, is equal to 4 by 3 pi r cube. 4 by 3 pi r cube. So the value of unit cell is equal to the volume of unit cell is equal to a cube. So if a is equal to 2r, then it should be 2r cube. It should be 2r cube. For the then after we applied the formula of packing efficiency, so packing efficiency is equal to volume occupied by atoms. So volume occupied, the single atom occupy, that is your 4 by 3 pi r cube, volume occupied by the atom, and volume of unit cell, that is your a cube, which is similar to 2r. So the putting the value 4 by 3 pi r cube divisible by 2r cube. Again 4 by 3 pi r cube divisible by 2 is 8 r cube. This r cube cancel. 4 by 3 pi divisible by 8. So if you solve this equation, you will get 52.4%. That means in simple cubic cell, the packing efficiency is 52%, and the vacant space is equal to 100 minus 52.4, that is your 47.6%. 47.6%, that is that area which is unoccupied in simple cubic lattice. Is that clear? 47.6. Is that clear? So this is for simple cubic cell. Now the next is, after simple cubic, we talk about for face cubic center. Second one is for face cubic center, FCC, or face cubic cell. So in this type, again we draw a cube. There are 8 corners, along with in each side one extra dot represent the number of atoms present in each faces of the cube. If this is your cube, so the arrangement is just like this one. This is total A, distance of any two lattice point. This one A, this one B, and this one C. So if the spherical portion is like this, so this sphere must be present in a diagonal, and if you draw the structure, you will get 3 points, that is your A, B and your C. This is your length, which is A, this is your base, which is also, and this is your tangent place, which is equal to, this one is R, this one is R, and this one is again R. So how many R is there? 4 R. So for this, the value of should be this there. If you see, look at the structure, what you get? The value of AC is 4R. The value of AC is 4R. So before that, we found that AC is equal to 4R. AC is equal to 4R, and the distance, and this point is known as B. If we suppose that B, otherwise there is no need. So by applying Pythagoras theorem, okay, so let us calculate the edge length, calculate the edge length of A by applying Pythagoras theory. AC square is equal to AB square plus BC square. AC square equal to AB square plus BC square. So the value of AB is equal to A, so there should be A square, which is also A square. This one is AC square, and the value of AC, we know that AC is equal to 4R, so this one is 4R square. This one is 4R square, so 4R square equal to 2A square. 4R square is equal to 2A square, or 4R is equal to under root 2A. 4R is equal to under root 2A, or we say that A is equal to 4R divisible by 2. 4R divisible by 2. Okay, 4R is divisible by under root 2. Okay, or we also write that 2 root 2 A is equal to 2 under root 2R. We can also write that. So volume of unit cell, what is the volume of unit cell? So volume of unit cell, that is AQ. So by using this formula, 4R under root 2 whole cube, 4R upon under root 2 cube. Okay.